Hi everybody, it's Mr. Duffy. Welcome to Physics. Today's lesson we're going to be talking about friction. Now, I know we've talked about friction in previous lessons, but in this lesson we're going to dive into a little bit more about the specifics with it and doing some calculations with the concept of what's called coefficient of friction. We have not done anything with that before in the past, so this will be all new information to you. So go ahead and get started. So according to Newton's second law, force equals mass times acceleration, and anytime there's a net force, there must be acceleration occurring. So one of the things that I like to bring up is if you're like riding a bicycle, why does a cyclist have to keep pedaling on a flat plane? Again, if they're just going on a flat level road, why does the cyclist have to keep pedaling? Because again, the cyclist would be applying a force, and according to that, they would again be accelerating. But again, they could just not apply a force and continue at a constant motion. Well, we know that that is not the real life scenario. The answer to that is friction. There's friction involved. So because the cyclist, again, is moving through air, or there's a rubbing between the gears and rubbing between the wheels and the road, there's going to be some friction in the reverse direction of its motion. We are not living in a world that is frictionless. Again, if this object was in space, it would just continue doing what it was doing. But again, in real life, we have friction. So friction is always a force that acts in the opposite direction of motion, and the cyclist has to constantly fight against the friction from the air, the gears in the bike, etc. If the person's pedaling harder than the friction force, then that cyclist would be accelerating. But again, if they're equal to each other, if there's no net force, then that cyclist can just continue at a constant motion. It really just depends what the cyclist is doing, but if they're equal in equilibrium, then it's just moving in constant motion. Now, friction force always works in the opposite direction of motion. That's never going to be a question. Friction never helps out an object. But there are different types of friction. Again, fluid friction, air resistance, rolling friction, those are all different types of friction, but every type of friction has what are called static and kinetic friction. Static friction is the resistive force that keeps an object from moving in the first place, and kinetic friction is a type of friction in which case the object is already moving, and it just kind of, again, inhibits that motion. So kinetic friction is always less than static friction as well. You probably have some everyday experiences with that. It's harder to get something to move than it is to keep it moving. If you've ever moved furniture or something like that, you would probably be aware of that. But this is kind of demonstrated here in this orange juice gallon. And so again, it's just sitting there by itself. There's friction between the orange juice container and the table. If somebody starts pushing on it, that's what's called static friction until it gets to the point where it starts to move, and then that static friction turns to kinetic friction, in which case, again, the static friction was more than the kinetic friction that is when it's moving. Okay? Now, whether it's static friction or kinetic friction, the friction force is related to the normal force. The friction force is related to its normal force. So, example would be like if we have something that's heavy and something that's light. I'm going to use a rock and a feather, but they're not always the best examples. But anyways, something that's heavy and something that's light. There's always going to be more friction force from something that is heavier compared to something that is lighter. And that's kind of because the normal force is also going to be larger. The normal force is the force pushing back up on that object. And so again, if there are, again, two identical objects, would be a better example, like a large rock and a small rock, there's going to be more friction force on the larger rock because there's more weight pulling it down, also in turn then more normal force. To remind ourselves what normal force is. Normal force is the force pushing back up on an object from the surface of that object. Okay, so again, normal force and friction force are definitely related to each other. But also what is related is what the surface is. Now, different surfaces have different, we'll call them slipperinesses or different amounts of friction, I guess. Stickiness, you can say it as well. And instead of saying, again, stickiness, when we're talking about this in physics, we would say the coefficient of friction. So different objects have different coefficients of friction. It basically relates how sticky or smooth the material is. It's a ratio of the friction force to that normal force. So again, different materials have different friction forces and so forth, different coefficients of friction. And that's because if we take a look at the simulation I've got here. Okay, friction is always caused by interactions between, again, two different objects that are rubbing against each other. Here I've got a chemistry book and a physics book rubbing against each other, or they're going to move against each other. And you can kind of see that there are these like small bumps, hills, and valleys on the surface of the material. Even if a material seems like it's really, really smooth, there's always some kind of imperfections in the surface. And as they kind of rub past one another, those surfaces can interact. And so I can move the physics or the chemistry book back and forth, and you can kind of again see as they kind of like interact with each other, that's causing a friction force, which in turn is actually, there's a thermometer off to the side that is also causing an increase in temperature. You can see the molecules kind of moving faster and faster and faster and faster because they're, again, heating up. Try this at home. Rub your hands together. Friction force between your two hands causes the temperature to warm up. Again, that's actually one of the ways heat was discovered in the first place. What was his name? Sir Humphrey Davy took 2 blocks of ice and rubbed them together, and again was able to turn them back into liquid water. And he found out that a substance which was called caloric at the time, which we call heat, is not an element, but a product of the motion of particles. So again, it's a temperature. It's not an element. Anyways, that's chemistry. But friction is caused between the rubbing of those two particles kind of together. Okay, how do we relate it? The ratio of forces, the static force over the normal force, or the kinetic force over the normal force, or again, if we're given maybe the coefficient of friction in the problem, we would multiply the coefficient of friction times the normal force to get the friction force. So again, it's really kind of depends what we're going for, but you have these on your equation sheet. Now, like I said, different materials have different coefficients of friction. We can think of them as like different stickinesses. Steel, kind of bumpy for the most part. Again, it has a coefficient of friction of 0.7. Rubber on dry concrete is about 1, so super sticky, which is why tires are made of rubber. Glass on glass is very sticky as well, so a coefficient of friction of 0.9. Things that are very smooth, on the other hand, let's see, ice. On ice, so 0.1 is the coefficient of friction. Our joints in our bones and our knees and so forth, 0.01 is the coefficient of friction there, which is, again, obviously it's super important so our joints in our bodies don't wear down. Now, again, this kind of illustrates something that I haven't really said. Coefficients of friction higher, closer to 1 would be the highest you could have, are the stickiest type of materials, the highest amounts of frictions, and lower, again, closer to 0. Again, 0 would be the lowest you could possibly have, but that's not possible. Those are the smoothest materials. So in every circumstance, though, we can kind of see that the static friction force is higher than the kinetic friction force. That's, again, the case in every single one of them. Some of them are the same, like Teflon on Teflon are the same, but I think that's just like a rounding error, or like they need more decimal places there to kind of compare them a little bit better. Still, anyways, that is coefficient of friction. Now let's do some problems. A 24-kilogram crate initially at rest on a horizontal floor requires 75 newtons of force to get it into motion. What is the coefficient of static friction? Okay, so coefficient of static friction, mu static, that's mu is what that symbol is your friction force over your force normal. Now, we don't have really either pieces of information, so it might be helpful to draw ourselves a free body diagram and relate what forces we have involved. We have weight of the object, gravity is pulling it down. We have the normal force pushing back up. Again, that would be the normal force pushing back up. They're equal and opposite. The weight down is the normal force back up. And again, we have object being pushed. It doesn't say which way, so I'm going to just assume it's being pushed to the right. We have a force applied of 75 newtons. That one is given to us. And we are going to have a friction force backwards. Okay? Oh, sorry. friction force backwards. Throw the arrow point right. Now, that is all the information it gives us, but we can draw some more information out of the problem. The weight is related to how much gravity is pulling it down, and so that would be mass times gravity. It does give us the mass in the problem, which is 24 kilograms, and so we do know gravity as well, so we can figure out the weight of this object. Okay, again, let's just do that. We know that the normal force is equal to it, so 24 times 9.81 is 235. So we have 235 newtons down from the weight. That means we have 235 newtons back up. Okay, now the other one that's a little bit less obvious is that this is the friction force is actually going to be exactly the same as the force applied. Now the reason for this is because the forces are equal and opposite according to Newton's third law, and it's equal and opposite until it again started moving. So the maximum amount of force was right at the instance where it started to move, and that's kind of what's going on here. It says in the problem, the force getting it to move was 75 newtons, and so that must have meant there was 75 newtons pushing back on it at the instance that it changed from being static to then going to kinetic friction. Okay, well, that is all we need to know to be able to solve this problem. The 75 newtons is our friction force, and our normal force is 235. So 75 divided by 235 is 0.32. That is our answer. Now there are no units to coefficient of friction because it's a ratio. 75 newtons over 235 newtons. Newtons and newtons both cancels out, so this is again just a ratio of forces telling us how sticky the material is. Coefficient of friction. Okay, now the crate in the last problem is now in motion. It's now changed into kinetic friction. The horizontal force of 53 newtons now keeps the crate in motion at a constant velocity. What now is the kinetic friction force? Well, let's draw a free body diagram of that again. So now we have a force applied, and now that force applied is 53 newtons keeping it in motion. That means the friction force backwards, it's also in constant motion, is also then going to be 53. From our previous problem, the force gravity, or the weight of it, is still the same. It's still the same crate. So it's 235 newtons down. The force normal then back up is going to also still be the same, 235. That has not changed. And so it really just kind of changes, and now we're going to changes the numbers. Now it's 53 over 235, and 53 divided by 235 is 0.22. 0.23. And that is the coefficient of friction. Again, comparing the last problem, the coefficient of friction before was 0.32. This one is now 0.23. So the coefficient of kinetic friction is less than the coefficient of static friction, just like I said that it would be. Okay, now, again, in this problem, I drew the free body diagrams, which are always going to be helpful in these types of problems. But what if we are given a free body diagram to solve for, and then that's kind of it. We kind of have to interpret the free body diagram and then solve for some missing information. You will have problems exactly like this on the worksheet that goes along with this assignment, or this video. So, again, free body diagram. All I can tell from this diagram is that we have a gravitational force of 12 newtons pulling down, normal force pushing back up, equal and opposite, 12 newtons, 12 newtons. Applying a force to the right of 30 newtons, and we have a friction force to the left. But again, we don't know that amount. We do know the coefficient of friction is 0.5. So we need to find the friction force and the acceleration to be able to solve this problem. Okay, well, the only way we can solve this is by solving for the friction force first. Can't solve for the acceleration until we have a net force, and we need to have a net force, we have to have that friction force. So if we remember, the coefficient of friction is equal to the friction force over the normal force. Well, if we have our normal force and we have our coefficient of friction, we can rearrange it so that friction force equals our coefficient of friction times our force normal and plug our numbers in and solve for that friction force. So the friction force is, the coefficient of friction is 0.5 and the normal force is 12. So that means our friction force here is going to be 6 newtons. 6 newtons right there. Okay, so our friction force is 6 newtons. Now, after that, we can now find our net force. It's the sum of the forces. Again, the vertical forces cancel each other out, but I have an applied force of 30 newtons to the right and 6 newtons applied friction to the left. So my force net is going to be, my sum of my forces, I really should just say, is going to equal 24 newtons to the right. Okay, now I can apply F equals ma, Newton's second law, to that to solve for my acceleration. If I'm solving for my acceleration, I would rearrange it and it'd be my net force divided by my mass of to solve for my acceleration. Oh, but I don't have my mass. Okay, I think we have to make the assumption that we're on Earth, which I think is a fair assumption to make. And we can figure out the mass by dividing our gravitational force, our weight, by 9.81. So 12 divided by 9.81 gives us our mass, which is 1.2 kilograms. Now we can solve the problem. A equals our net force, 24, divided by 1.2. And so that comes out to be a, well, I rounded it. It comes out to be 19.6 if you keep all your decimal places. Otherwise, it would be again 20. Okay. So, anyways, that is our acceleration. Sorry, not newtons. 20 meters per second squared. 19.6 meters per second, and that would be to the right. Okay. I know this video is a little bit longer than normal, but hopefully this makes sense to you as to what friction is and a little bit more detailed calculations. And hopefully it makes sense this new concept of coefficient friction is really just, again, a measure of how sticky the materials are that are interacting. So, thank you very, very much for watching, and hopefully this was helpful.